here. Okay, so we'll go. No, 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 no. So let's go with English, no problem. I just need some water for that. Okay, so hello, my name is Grzegorz Mazur, and I will tell you about AI in video games. Okay, so maybe more questions. Who is doing already some games from you? Are there any Okay, okay, that's cool. So maybe first who we are. We are Vile Monarch from Warsaw. Or maybe so someone knows us already. Okay, good, good. So that's why I'm here. So we started the company 2.5 years ago with my friend after we left 11-bit Studios after doing This War of Mine. Maybe you heard about this game. So far we put out a couple of small games. First was Crush Your Enemies, which was tiny RTS game, which will be also a topic for today. The second game was also the Insult Simulator, so far our biggest success, where two gentlemen try to insult each other without using curse words in a Monty Python style. And the game was that successful, then we created the next game in the series called Oser the Hollywood Roast. So this is our latest game. Now we are working on some bigger games that are still not announced, but we will announce them and release one of them next year. And again, it will be something totally different. So who am I? So I'm one of the bosses and a so-called technical director at Vile Monarch, which means I was programming, but I don't do this because I don't have time anymore, so it changed a bit. So previously I was working in 11-bit Studios, as I said, as a lead programmer of This War of Mine and Sleepwalker's Journey. I am also, actually I'm not anymore, lecturer at Warsaw Film School where I was teaching game programming in Unity. I'm a mature musician. Here's my email and Twitter if you want to talk, do business, or work with us. Feel free to contact. So yeah, these were the games that I did in previous company. So This War of Mine was the most known, I think, so far. So okay, today I will talk about AI. So I won't talk about, of course, everything because we don't have much time. I will only tell you about general approach we have in games while doing AI, what approach we had in This War of Mine or Crush Your Enemies or different games. And a couple of techniques we used, because there is no one way of doing AI in video games. Every game needs its own way to approach this topic. Okay, but first we should talk about what this AI actually is in video games. So I say that it's an interactive system that animates game world. Interactive, which means that if you put a guy on a level that will run in circles, it's not AI because okay, it moves, it does something, but it doesn't react to what player does, and it should. So that's how the system works. You always find this AI agent thing in every game. AI agent will be the entity that can make its own decisions and do some actions in a game. So it can be different thing in every game. So in This War of Mine, for example, it was a single character. In RTS game, it can be a single soldier or a whole army or a whole, I don't know, squad of soldiers. It depends on the game, depends on the scale, so we have to find it in every game from the beginning. What is this single AI agent? So agent, based on his state and game world state, takes actions. So this sounds simple, right? So it can be something like this. So AI system can be like the box where we put two things and we have one output, right? So these two things are different stimulus. Like, for example, seeing enemy, hearing call for help, taking damage, or whatever different you have in your game. State of agent can be level of health points, resource quantity in RTS game, or current goal. So current goal is something special, but I still considered it as a state of agent. Every AI should have some goal. It can be, of course, destroying the player, but it can be something different, like defending the room or gathering some resources or something like that. So it also depends on what we want to achieve. So based on these two things, AI takes actions like shooting, playing animation, beginning of movement, commands to move your troops, whatever. So what's important? We have to find all of these things like stimuluses, state of agent, and action in each game, because each game has different things here. And so we start basically from this. We look for this, what inputs we can have, what state we have, and what actions we can take. What's important, we should always give the same actions to the AI as to the player. For example, AI shouldn't have more possibilities than player has. Because if AI can do something that player cannot, and player will see it, he will feel cheated, and he won't like the game probably. So this is the mistake. So for example, if we cannot shoot through walls, AI shouldn't also shoot through walls. But on the other hand, we can also, of course, cheat as doing AI. So AI can, for example, have more knowledge than the player has. But still, we should do this in a way that player doesn't see it, because in other case, he will feel cheated. So we should be aware of that. So I don't know, if we have a racing game, if we cannot make, I don't know, some curve in a specific speed, then the enemy car, like an AI car, shouldn't also be able to do this. This is really important. So yeah, so basically we look for all the actions we can take, for all the inputs, for all the state, and then we think, okay, how we can connect it, and we should find a system that we put inside. So as I said before, there's no one system, there's no one way of doing this. We have to find it. We have to find good tool for our specific game. And I will show you a couple of these. Okay, so now we know what this AI is. Now we should think about when we think AI is good. So I see two approaches here, like good for player and good for developer, because it's not the same thing. And this is, I think, really important. What makes AI good for player? It should support gameplay, which means it should create specific challenge or support storytelling in our game. That also means that good AI doesn't have to be really smart, because we shouldn't create like a perfect AI, because if you create like a perfect AI that plays our game in a perfect way, the player will always lose. So, and there's no point in that, because the game will be really frustrating. So the game shouldn't be too good. The AI shouldn't be too good, actually, in most of the cases. It just should create good challenge. So probably even we can put more like a stupid AI in the beginning of the game and then make it more smart later in the game. This is the thing that we did in Crash Enemies. It was like basic AI on the beginning, and then we switched on some more tactics, more cool mechanisms in AI to make it more intelligent and harder to beat. So this is really important. Our goal in doing AI in games is never to make it as good as possible. Maybe besides some games, I don't know, some FPSs where we do some, I don't know, tournaments against AI. In this case, probably AI should be as good as possible, but in most cases not. So in this war of mine, Crash Enemies, our goal wasn't to make this as smart as possible, but to support gameplay, challenge, and storytelling. So that's really, really important. I even see that sometimes if AI is actually stupid, people still have fun with this, because when we find that, okay, AI did something stupid and we re-record the video, players put it on YouTube and have laugh about it and share it, in many cases it works good for the game, because it even promotes the game. So it's not that bad if the AI is not that smart. Another case when we shouldn't also be scared of doing AI that works like a bit schematic. We shouldn't be afraid of situation when player, after, I don't know, spending a couple of hours, will find a scheme on which AI works. Because finding this kind of schemes is also fun for player. If player will realize how the AI works, it's most of the cases it's fun for him, because he will feel really, powerful and really, smart that he found how we did it. So it's also not a big problem. Yeah. Okay, so what makes AI good for developer? I hope it's obvious. So of course it supports gameplay, so it is good for player. But also should be configurable. We should configure as many things as possible, so hard coding AI is not that good, but we still do it in some cases. It should be predictable, so maybe this is not obvious. Predictable for developer, which means if game designer will think, okay, in most situations I want my AI to work like with some rules, But in this and this situation, I want AI to behave especially like I want. Like, for example, a soldier normally tries to attack us, but for example, in these specific rooms or on this level, soldier has to always do something else because it will support my storytelling, my story I try to create there. So the system we built for AI for our game should support such situations. So in Crash Enemies, we didn't have many situations like that, but in this War of Mine, there was a lot of this because we had a lot of story to tell there. So in general, designers wanted to have a tool that will allow them to create some rules, but in specific situations to force some specific actions. This is really important. So game designer always have to be able to see what will happen from the design he will do in an AI tool. Reusable. So I don't know, if you create like a couple of behaviors, we should be able to reuse it in other characters with some slight modifications, and scalable in every way. So if we create like a behavior for one character, then running 2 more characters should be also possible from performance point of view. And of course, if you will create, this is more important, if we create like, I don't know, 10 behaviors for one character, then adding 11th behavior should be also doable and easy. So it's not possible in every solution, as I will show later. So I will repeat it again. There's no one solution to achieve all of these goals, and there's no one solution to connect all of these things we have in our game. So with every game, we approach it from the beginning, from scratch, and find the best system to solve our problem. So now I'll show you how we solve this in a couple of our games. Of course, it's not all. These are not all possible solutions. You can also always use all of them, like connect them together, or use only one of them, or come up with something different. So I will show you only like the most popular, I think, as well. These are the things that we used. So first is quite obvious and easy to start with. It's like really simple scripts, if something, then something. Like if I see the enemy, I will chase him. If the enemy is in range, I will shoot. Like event-based programming also. So it's really easy to start with. We can really start with quickly and fast. It's really easy to customize a lot of things because we can write whatever we want. Only code limits us. But the problem is with the scripts that it's harder to predict everything, because it's hard also to create emergent AI, emergent that we create some simple rules and they all together work like a more complex system. It's harder in scripts. Of course, in scripts you can do actually everything, but it's a bit harder if you don't have like a visual tool or something like that, and becomes drastically complicated with size when the AI gets more and more complicated. And the probably most obvious downside of this approach is that it can be done by someone who knows how to program, right? So in most cases, in a game dev studio, we have programmers, we have designers, artists, and so on. So not all designers know how to do scripts, and if they do, probably they don't do this really good. So in most cases, in most companies, the programmers prepare tools, and the designers use these tools to create the AI or a gameplay. So in that case, we need a programmer that will do it, or a really good technical designer, which is not that popular position. So yeah, but still, it's a really good approach for simple games where the AI is really simple, when we don't need to manage like more complicated tools. It's also great for prototyping phase, for a pre-production, because when we prototype the game, we usually don't know how the game will look later, because we are checking the idea. So there's no point in building the big tools, because it will be a waste of time probably. So on the prototype level, the scripts are doing really good. So we did Crash Enemies prototype, and even this War of Mine prototype that way, that we had like simple scripts that were okay in most of the situations. In some edge situations, they were really stupid, but it was enough for a prototype to check if our idea for a game is fun and cool or not. So yeah, so this is good for simple games and for prototypes mostly. Okay, so the thing that solves this problem is finite state machines. I hope that everyone knows what it is, because it's really simple, right, and basic thing. We also use it for AI. So, in every moment, agent is in a specific state. So this specific state can be a specific behavior. So in an example from the game, it can be like combat, retreat, like looking for enemy, running away, or whatever we have in our game. So every state is a specific behavior. Under specific conditions, agent can make transition from current state to another, right? So this is really simple. So the cool thing about finite state machines is that we can show it visually, of course. So we can create an editor for that in our game engine, or buy one, or editor, or our game engine already has it. So this is really cool for designers, of course. So programmer can prepare like these blocks only, the scripts that run the behavior. So every behavior can be a script. And yeah, later we can do these transitions, of course, give some parameters, put parameters to the editor that designer can change by himself. So this is really much better because, of course, it's visual. So yeah, in this example with 4 states, we then think about from which state to which we can go and under what conditions. So for example, from idle to following after enemy, we can go when we see the enemy, from following after enemy to combat when the enemy is in the range of combat, and so on. From combat to following if the enemy is out of range, from combat to retreat when our HP is below some level, and so on and so on. So we can come up with all the rules that we want and create them as a state machine. So this is really cool. It's really good for designers also. It's easy, of course. It's easy from idea point of view. But there's a problem with complexity. So finite state machines works great when there is not many states. Because if you add like 5th state, like for example, different combat, like close combat, for example, which has different behavior, and we can come in the state under different conditions. So of course we create this 5th state, then we put it in a state machine, and we have to analyze actually all of the states we already have, if we can go from this state to the new one or not, and on what conditions, and way back. So if we put the 5th state, we have to think to what states we can go from the 5th one. So when we add the 5th one, it's not like a lot of things to think about. But let's imagine we have like 100 states, and we add like 101st state. So this is a lot of things to think about, a lot of possibilities to make a mistake, and it's really, really bad. It's really complicated, and it's really hard to manage. So finite state machines work really, really good. Like we have 10, maybe tops, like 20 states. Not above that because it gets too complicated. Yeah. So yeah, this works great for like a bit more complex games, but still not very, very complex. So we used state machines for another prototype for the game we did before this War of Mine, but the prototype was failed. But still, we had more complicated AI, and finite state machines were working good as long as it wasn't too complicated. So we are looking for a way to solve the problems we had with finite state machines, because there are a lot of good sides about this, of course. And there's a thing called behavior trees. I think this is the most popular, technique, way of doing AI in video games. It is used in small games, in a really big AAA games like Halo, Witcher, and so on, because it solves a lot of problems that finite state machines have, and still have many good sides. So I will sum up it later, but first let's talk about these behavior trees. So I also assume that everybody knows how the tree looks like. So we have nodes. Every node is a complex behavior for our agent, and each node knows if it can run or not. So if we have node for a combat, this node we can ask like, can you run or not? And combat say, I can run because I see enemy or something like that. Of course, in code. All of this is done in code. So when node is running, it tries to run its first runnable child from left, right? And that's how tree-based decision structure appears. And at each moment, only one branch of the tree is running. So To show it on an example, I did a really simple example similar to the previous one, how we can do the same AI with a behavior tree. So we have a root node, and root node have 3 nodes in this case. Each of them is like some behavior, like combat, following after enemy, and idle. So as I said, when we start to run the tree, each node knows if it can run. Root node always can run. So if root node can always run, it starts running. So it starts to run first of the runnable child, of its children. So it asks from the left each of the child, and first that it can run, it will run. So enemy asks combat, can you run or not? Combat says, for example, yes. So the combat tree will, subtree will run. After combat will finish, the enemy will finish, and the whole tree finished its running, and we can start the tree from the beginning, running the tree. But if the combat says, no, I cannot run, then enemy will try to run following after enemy. If following after enemy will say also no, for example, it will try to run idle, and so on. So in this case, we can assume that idle is always yes, can always run. So in case that combat cannot be run and following after enemy, then the idle will run. So it works basically like that. But of course, we can build as many levels as we want. And this is where the power comes from. So basically, in behavior trees, we don't build like a big nodes like combat following after enemy, but we have like a couple of generic nodes, like selectors, sequencers, which I show you now, and action node that do really atomic small actions. So in this case, idle can be a sequence. So it is shown by this arrow, horizontal arrow. So when the enemy is selector, which runs the first runnable child and only that, then sequence runs all of its children one after another. So idle can be a sequencer that has like a couple of action nodes, like choose random point of interest, then move there, then play some random animation, and then wait for a couple of seconds so it will look more real. So if the idle will start running, it will run this sequence and run all of these actions. After it will finish, the whole tree is finished because there is nothing more in idle, and that's all. So, so that's how actually we build these trees. So let's see at combat, because with these action nodes, which are always the leaf nodes. In a tree, we do actions. But also let's see how we can check conditions, because I said that every node knows if it can run or not. So also we don't program like a big node combat that says if I can run or not, but we do like more atomic checks, conditions, and so on. So for example, we can create a decorator. So we used also decorators, which decorate some actions below. Decorators we can use for also actions, but also for checking conditions, for example. So we can have a decorator that checks if enemy is in range or not. So the combat can be just a decorator that checks the condition, and then we can have sequence that does sequence of actions, so playing animation and dealing damage in this case. So this node combat can be not here, like we can delete it, of course. It can be directed this one, but I just put it to have this label combat. So that's how we build the trees. So we have like decorators, we have actions, we have selectors, we have sequences, and this is basically it. With this, we can build like really complicated AIs. We can of course add more different nodes. We can have like sequences that work in a different way. We can actually use selectors that are parallel, that we can run some parallel subtrees if you want, but it's like more complicated. So what's more with this? The problem is here, like if we run this idle sequence, for example, is what will happen if the enemy will see the, I don't know, player at some moment in the middle of the sequence. So in a basic way, in a basic option, the sequence will finish running. After it will finish run, we'll start tree from the beginning. So the enemy will check if the combat can run, and combat will see, oh, I see the enemy because I have this enemy in range. So the combat will start. So if you are in the middle of the sequence, it will take a lot of time, so the AI will be not responsive. So what we do to solve this is that we reevaluate all the conditions in a tree, like every tick, every update, or every second, for example. So even if you are running some tree, subtree on the right or in the middle, selectors should always check the conditions on the left, if they are like met or not. And if yes, then the tree can interrupt running current subtree and go to the more important one. So that's how we can create responsive AI. So yeah, it's reevaluation. So basically, behavior trees are like hierarchical finite state machines. So what's cool, we can show, we can recreate every state machine as a behavior tree, or every behavior tree as a state machine. So it's not like behavior trees that give us something more, but they just organize everything in a different way. And of course, what's great, it's also visual, so we can have an editor for that. So like every engine has it already, like Unity. Oh, Unity actually doesn't have it. We have to buy or download an asset for that, like a plugin. Unreal has it built in. In our engine, in this war of mine, in previous company, it was our own engine, so we didn't have an AI system for that. So we created the editor and behavior tree engine from scratch just for that. And it was really easy because, as you see, the idea is quite easy. So from programming point of view, it's easy. So the more power is given to designers, so we as a programmers actually have to create all of the action nodes, the leaf nodes with all the actions possible for the game and with a configuration for this, and all the decorators to check the conditions, and that's all. And we give it to the designers, and they can create really, really powerful behaviors, powerful AI. So basically, you have like a visual editor. You can have library of different nodes you can use. What's more cool about the behavior trees that these are trees, so it's really easy to make it hierarchical. So you can build like sub-trees with simple behaviors, then connect them to bigger trees to have more complex behaviors and so on. So we created like a library of basic behaviors that were just trees, and then when we were creating new character for the game, we are just taking the behaviors from our library, connecting these in a bigger tree, and it was working. So it's really cool. So the problem of size. So as I said, with state machines, when you have more states, it gets more complicated and hard to maintain. With behavior trees, our most extreme example was like tens of thousands nodes in one tree, and the one designer was still able to to manage it, and actually he was working alone on this. So because you can divide this big tree on a subtrees and so on, this works hierarchical. So even if you have like tens of thousands of nodes, it's manageable for one person, and it's doable, and it also runs fast enough. We even put it on mobile. The game was working on mobile phones fast enough, so this is really good. So if I would have to choose like most popular and most powerful way of doing AI in video games, I would say that these are behavior trees. That are also most popular, right? So as I said, smaller games like this War of Mine were using this, or big games like Witcher also use this. Because it's really good for smaller and bigger games. Of course, if you have a really small game, like a really simple AI, behavior trees can be too big. So we have like state machines for that, or even scripts. So okay, so behavior trees are the most important, I think. So I will show you one more thing, because like behavior trees and state machines and so on, these things like let us design what decisions we make, what actions we take. But in many games, we have also different like problems to solve. Like in RTS game, for example, we have to solve a problem where we should send our troops. So we can, of course, have a behavior tree, for example, or a state machine to decide, okay, in this moment we should attack the enemy or a player. But the other decision is to make where we should attack. So behavior trees are not very good for that. So there are different ways. So I will show a really, really simple thing we did for crash enemies. It was, this is called influence mapping. And we used it to find areas where we should move our troops. So yeah, so this is really, really simple idea. So as you see, like most of these ideas are quite simple, but they are still really powerful, and you can do magic with this. So this is another example. So the assumption we have to make here is that game world is represented by grid or a graph. So in Crash Remis it was obvious because the game is based on grid. If it's not, if the game is not based on that, you just need like a different representation for AI, but it's not a problem. So AI idea is really simple. So each unit, building, resource, or whatever you have on your map, what is important, or a soldier on a map has its own base influence, which is only like a number, like float from, not even without a range. So it can be 0, 1, 2, 1.5, and so on. So value and area. Yeah, so I will show you on the scheme in the next screen. So then what we do is like calculating map of our influence and a map of enemy influence. So map of our influence is just going through all the cells in a grid and adding all our all influence from all our units, buildings, and so on to each of the cells. And then we do the same thing for enemy in a different map. So then what we calculate is influence map, like a total influence for a whole map, is like subtracting our influence map from enemy influence map. So it can look like that. For example, if you use colors for visualization, so for example, the more orange the color is, the bigger influence is, the higher value is above 0, and the more light blue, the more below 0. So the higher value is, the bigger enemy influences. The smaller value there is, the higher influence of us. So as I said, every thing on like unit buildings have its own influence. So it doesn't have to be only on the hex or on a cell that we stand at, but it can be also, in a bigger area, so we can have like some value on a cell we stand, the smaller one on more distant ones. So that's how we can model how our units influence its surroundings. So for example, for a simple example, peasants have like 0.5 on the place they stand, and only that. Soldiers have like influence of 2 where they stand, but 0 around. Archers have 0.5 where they stand, but they have, for example, 1.5 around, because they can deal more damage in a distance, but really small damage where they stand, and so on. So that's why we can model how all the units, buildings, and so on influence the map. So yeah, so when we calculate the influence map, the solution here is really simple. So if we want to send our troops somewhere to do some damage for our enemy, we just find the place with the highest weight. And the weight is just influence of this place divided by cost of moving our troops in that place. So this is really, really simple. So of course, cost is like a length of the path to that place, and with some modifications, like if you have like different I don't know, types of terrain, like swamp or forest or grass or road that you can move on with a different speed, then we can also put this in an equation here. So where we send our troops is just the biggest influence divided by cost of movement. And so it's like 2 hours of programming, and if you start this and just put it to run, it will actually work. It will look like smart decisions, because AI will send like will ignore really small units that are close to us, because this is not a threat. It will send like for a bigger fights, but more far from our base, and so on. So it can eventually attack the base of our enemy and destroy it. Of course, there are some edge cases that it won't work, but in a really basic way, you can do even for a prototype of the game, something like that, and it will just work. And this is something that player can play with already. So this is really simple, but you can, of course, improve it and expand it. So you can create more mapping in that same philosophy. So you can create this tension map, which is not like subtracting influences, but adding them. And this gives us different information. Like the higher value is, the bigger forces at area there are. Doesn't matter if ours or the enemies, or together, it will be even bigger value. So from that, you can create the index map, vulnerability map, which is tension map minus absolute value of influence map. So this is really cool map because the higher value is, the bigger like even fights are there. So we know that we lose a lot of forces, a lot of troops in that place, and enemy also loses a lot of troops there. So this is, for example, a good place to send like, I don't know, the healing units if we have such units in our game, or a build turret there, or buildings that will help our troops, because we are losing a lot of money there, but it doesn't move like a front of fights. So we can create like many of these maps in a really simple way and like gain a lot of information from that and base our AI on that. So based on information from different maps and additional conditions, we can create like any strategy. We can go even further. We can introduce inertia or propagation of influence. So if the enemy will die or units will die, we don't have to like put the influence to 0. We can make it like a flow to 0 after some time. So it will have like a memory of previous fights. This is really cool. We can propagate influence. If the enemies stand in some place for a longer time, the influence grows because the area is getting more and more like defended. So this is really also cool idea and really simple to do. Designer can introduce his own additional goal map. So designer can actually paint on this map by himself. If you want to, for example, make AI defend some place on our level, designer just have to know to add some numbers to the influence map, and AI will automatically put some forces in that place and try to defend this place without like additional conditions, additional scripts. It will work just with these maps. So what's cool, we can have these maps and create like really simple scripts that use these maps as a source of information and run our troops with this script. So, and this is where the connection of two techniques comes, right? So we can have influence mapping and really simple scripts, and all together it can do really powerful thing. So this is how we did this whole game. Like we have different troops. So game is really simple because we like put the RTS experience to small battles that last for 5-10 minutes. So it's not that complicated as a big RTS, but still we have different units, we have resources, we have to do some tactics, strategies. So this is the problems that we have to solve in every RTS game. So with this influence mapping and just simple scripts, like different scripts for different types of units, we created AI that works emergently on actually every level we created. So there was also no need to tweak the AI on different levels. On different levels of the game. So this is really cool. So we can also have different scripts based on difficulty level or how far we are in a campaign, as I said, to change the difficulty for the player. So yeah, this is also quite cool technique, as you see, really easy and really powerful. So yeah, we are running to the end. So I have only like names that we can also check that are used with more or less successes in the video games. So we can have planners. So this is like a bit different approach when AI have different plans, and all the plans can have different weights based on the state of the world and state of agent, and it can like run for one plan or the other. BDI agents, belief, desire, intention. This is really cool, more from like academic point of view, because like there are not many games that use this approach. The only game that was successful and well known is Black and White game, quite old one. But it's a really cool thing to check if you are interested in AI. Of course, we can use neural networks, but like more like if you want to teach AI how to play as good as possible to beat the player. So it's not like an obvious tool for designers because it's not easy to to control. AI done on neural networks. You can also use fuzzy logic or connect all of these or connect these with the techniques I told you before. So yeah, there is a lot more to check and learn, but we don't have more time for that. So thank you. So do you have any questions? Because I think we have a couple of minutes. Yeah.
So you need a strict hierarchy,
Mm-hmm.
and what if you can't design a strict hierarchy work. So you don't always know that combat is more important for the AI agent than another thing. Is it
Yeah.
not a common problem? Or
Yeah, so this is the problem that happens, and it's a problem hard to solve in behavior trees. So behavior trees are not like perfect. This is the problem when in some situations you want one tree to be more important than the other, or the opposite in other situations. So this is the problem. In most cases, you know how to order them in a selector. So this is not a problem. When you will approach this kind of problem, we solve this like. If we needed that case, we put it like more like conditions and that we're calculating.
solve it always in an ugly way? A lot of conditional statements.
Yes, so you can, for example, if you know what the condition, what conditions change the order, you can just check this condition in both of the trees, these subtrees, and it will like change the order. So this is not very good way, but I don't